Hello, welcome back to another lecture on methods in experimental ecology. This one's going to be about box plots and standard deviations and standard errors and confidence intervals, and essentially asking the question on which one should you be using. Remember, the whole point of a lot of what we do in experimental ecology and biology in general is to try to assess the variation in what we're studying, whether that's the size and color patterns of frogs or the patterns and shapes and sizes of Japanese maple leaves, because yes, those are Japanese maple leaves, not something else you might be thinking of. Or maybe you're trying to evaluate the variation in some sort of mystical creatures you've been chasing around on the streets, like Pokemon. So if we're trying to evaluate variation, we need to try to represent that so that it conveys our story clearly, so we can present our results to somebody in a way that they can see the signal for the noise. Because remember, that's a lot of what we're trying to do in statistics, is to detect signal in among the noise, or the variation. So there are a number of different ways to do that. I'm going to select these as the perhaps leading ways to address variation. And in fact, as in Andy Hector's book on the new statistics, we can segregate this list, these sets of measures of variation, the different ways of measuring variation, into a couple of categories. One would be those kinds of measurements to record variation that are simply describing the distribution of the data, the variation in the data set, or in one data set, and then evaluating it separately in another data set, versus a different goal, which would be to help support or make inference on the data, specifically related to the kinds of statistics that we've already been doing regarding where is a mean. So is one mean greater than another mean? And the error bars being a way of saying that that mean is substantially more than another one. Okay? So there's the two main goals. One is just to describe the pattern, and one is to help out with making inferences about differences between means, and knowing full well that there's some variation around a mean. So here's an example, if you want to think about a really variable scatter plot. Just simply this alone conveys a lot of information. There are a lot of data points in here, and you could say it's really messy, but you can see that there's sort of a central tendency for a lot of points to run out through the middle here, with of course a lot of points way outside in the other edges. Some that are packed along this axis, some that seem to be arrayed in lines going out at other places. But there's a way you could present data in a scatter plot that might be simply able to convey a lot of information. Now, that doesn't help us with an equation necessarily, but it certainly presents us with a lot to think about immediately. So scatter plots, remember, are just presenting data in their raw form. They can be messy like this, but on the other hand, that itself can be useful to convey a story at times. Other times you might want to see a scatter plot, for example, superimposed on top of another category, the box plots, which we've already been playing around with. And so the scatter plot just simply presents every point within the range for any given set, like this group of names here, A, B, and C. And you can see how the box plots represent, to some extent, that variation in the scatter plots, okay? So they can be sort of an underlying or even overlying layer that helps represent a little bit more information. Now, it's fair to say that the scatter plots here are somewhat redundant with the box plots and not actually conveying a lot of extra information. But it's somewhat of a matter of artistic taste. It's whether you think they're useful to have them there. So scatter plots can also, then in other words, besides being the raw data, be a way to help inform a condensed version of data like in a box plot. And of course, in a regression kind of context, they help us see the actual pattern. And of course, drawing a line through this pattern is a matter of you judging whether or not that the line represents the pattern adequately. To be able to make that judgment, your eye needs to see the pattern or the raw data. So they help us in visualizations of regressions and your own mental assessment of what you see as a fit for that data. Okay? So scatter plots can be a really useful way to describe, again, remember, all of the data, the representation of the variation in the data. Now, box plots, of course, are a simplification of that scatter, where we've seen already that a box plot is essentially representing a bell curve on its side, if you will. There's a middle here, the median, and then the top of the bottom of the boxes are the quartiles, so upper 50%, lower 25%, right? So we've got 50% of the variation represented inside of a box, and then the whiskers going out representing usually the upper 90% and the lower 10%, and then some points beyond that being outliers. So there's essentially a bell curve represented with any box plot. And we can see that there's a variation in the temperature in January, but there's also a fairly typical trend where they're more or less around this middle, let's call it 7 or 8 degrees Celsius. And of course, we can evaluate that scatter of plots. If we want to show all the raw data, it might be fuzzier than this, but you'd still see the general trend underneath all those box plots, right? Okay, so the box plot is really a simplification of that raw scatter then, isn't it? And if you think about a box plot, what we're really doing is evaluating that data in a non-normal distribution kind of way. Now, another way to think about representing that data would be the standard deviation, where the box plot is not centered around a mean. Of course, the standard deviation is counting a distance away from a mean, assuming this nice normal bell curve around a mean. So the box plot had nothing to do with the mean. It's representing the median, and therefore it can be a little more skewy. Let me show you again. Some of these box plots are not quite centered, right? Some of them are a little bit off center, representing a skewy distribution for the mean. Some of these are, on the other hand, fairly simple and symmetrical, and those would have been representing much more close to a normal bell curve. So if we represent something as a mean plus or minus a standard deviation, the implicit assumption is that it does fit this nice normal distribution, and that you're adequately representing 34% of the variation on either side of the mean with your standard deviation. So if your data are a nice normal bell curve, this is a nice descriptor of that pattern. And just like the box plot, it is a simplification of what would otherwise be this scatter of lots of points packed up and down here. Okay, so it's useful to think about, how does this look sideways? So I'm going to take this bell curve and just turn it sideways and stretch it next to the one on the right that you see here, and it would look about like this. Well, remember, this is going out one standard deviation, and this is going out another standard deviation. So there's 2 standard deviations down, about to here, and about up to here. And the data would be presented as, even though it's a bar graph like this, going down to perhaps 0, there's some chance that you'd get some really small values down here. You don't have a negative price necessarily, but you might have some zeros. And there's also some chance you might have some really high prices for oranges. But remember that this error bar is actually representing only a portion of the total scatter of a data set. So when we represent these scatter plots as a simplification, you necessarily lose some data. The idea is that you can mentally retain some of that information and visualize this bell curve adjacent to a standard deviation like this. Okay? So the standard deviation is a useful way to present the data, and so is a box plot, the raw data version being a scatter plot. Okay, those are all for describing the data. What if we want to describe a measurement, a mean of a measurement, right? We might describe the mean of a measurement for this little guy's height right here, and we might want to measure it using this big piece of plywood that has the feet marked off. On the other hand, we might want to use a yardstick. Or on the other hand, we might have them stand up straight a few times. So we get these different kinds of measurements, and there's variation in those measurements. This one might be exactly 3.5 feet, but slightly other measurements might occur if we did it a few more times. So we get some error around our mean measurement of his height. Okay? So the inferential measurements that we're trying to do here would be to say, for example, get a good estimate of his mean with some variation in that estimate, and perhaps be able to compare that to another mean, his height next year or another kid's height. Okay? So there are a few different measures that we can use to help make inferences about means, recognizing that there's variation in the measurements of that mean. We can use the standard error, which is just a way of describing the variation between estimates of a mean, a 95% confidence interval, and another way describing the pattern differences between means, which is least significant differences. So let me walk through these, and I want to also help, I hope, explain the difference between standard deviations and standard errors, which seems to lead to some confusion. I myself find some of the terminology confusing, and I hope maybe this will help make it a little bit more clear. So let's return to this graph I showed you before that I lifted from this website, where they just simply show the standard deviations, as explained here, standard deviations in the prices for these different fruits. This over here is being a different set of bars, but the same means. So the same mean prices across here for each of these terms. Notice the only thing that's different then is the error bars. This is reporting these as the standard deviation of the mean. This is the standard deviation of the data, like I was trying to describe before. So standard deviation of the mean can also be known as a standard error. So this is where I think some of the terminology gets a little confusing. This is representing the variation in the estimate of the mean. This standard deviation is representing the variation in the data itself. So this is the average, give or take a lot of numbers around it. Oops. Whereas this value over here is as an error bar to describe where the mean itself is located. Okay? So what we end up with then is a set of different ways of describing where the mean is located. And this is some of the terminology I find confusing. So first off, try to make the distinction with a standard deviation. The standard deviation of the data, like I was just talking about for a while here, is the square root of the variance of the data, or just simply sigma, right? So square root of the sigma squared is just sigma. That is describing the data. A standard error is a standard deviation of a statistic. So a standard deviation of a statistic is calculated the same way as a standard deviation of the data might be calculated. So in other words, a standard error of the mean, sometimes also abbreviated as an SEM, is the square root of the variance, but then it's divided by the square root of n, the number of points, which is another way of saying the standard deviation divided by the square root of n. Okay? So we have a standard deviation of the data, or if you divide that standard deviation by the square root of n, that's like saying how much variation do you have on average per unit n. And why is it square root? Because it's square rooted in the numerator as well. So what we end up with then is something that's going to necessarily be smaller than a standard deviation. It's divided by a term, okay? And so it is essentially something like a per unit measure of variation, per unit on average kind of measure of the spread. So we associate that with the mean value because it represents the uncertainty in where a data point might be located, and we can relate that to where the mean data point might be located per unit, an average. So that is sometimes called the standard deviation of the mean, sometimes called the standard error of the mean, especially in R and in Hector's book, and also more commonly in the literature being called a standard error. So you see how there's some confusion in the terminology. I'm going to try to just refer to this as standard error, although it is also helpful to distinguish between the standard error, because that is of a statistic, and the standard error of the difference between means. So I'm sorry, let me say that again. There's a standard error of the mean, and there's a standard error of the difference between means. So if I calculate a difference between means, that's an estimate, and that estimate itself can have some noise around it, some variation. And so the variation of the difference between means, because a mean is not an identically perfectly measured thing every time, there's variation around a mean. That variation around any one mean means that I have some variation between means, okay? Hope that helps. So the standard deviation of a difference between means is an SED, and a standard deviation of a mean is just often called a standard error for short, okay? So you can tell there's a bunch of different jargon, and you can see all of these abbreviations used in different resources. I find that a little bit awkward. There's another reason why I find this to be a bit awkward, and let me just revisit the standard deviation then of the data versus the standard error, also known as the standard error of the mean, also known as the standard deviation of the mean, right? I think this is clumsy. But this is the point I want to get to besides the clumsiness of the jargon. The standard deviation of the data is saying I might have data points way up here, I might have data points way down here, although those would be pretty rare. Most of the data points are going to be sitting in the middle. This standard error is saying here's where the mean sits, but it might sit as high up as this, or it might sit as low as this. But notice that that's only representing that middle darkest blue portion. And just to read that mirror image over here, that's 34% and 34%. So this standard error of the mean represents 68% of the data. That's a fairly narrow set of the range we might have in a bell curve. That is less than what we often think about as a 95% interval or a 5% probability kind of thing. So this standard error right here is actually narrower than you might use to try to help make inferences from. It's a useful score to say how unsure are we where the mean sits, but it's not necessarily something that I find that helpful for inference. So it's related in that it's calculated from the same ways of calculating the standard deviation, just divide by the square root of n, and so it's assuming we have this normal distribution. But it's also a tad narrow for making inferences, which is really the point of standard errors. Let me see if I can help that way again. If I was to think about a bell curve, and there is this mean right in the middle, and I have a distribution of the mean. So the mean might be as far out as here, mean might be as far out as here. Remember, we're talking about inferences of a mean. That's different from where the data sit. Where might the mean sit? Really low chances it's way out high, really low chances it's way out low. So the mean should be sitting right here in the middle, and the standard error is representing 34% of the area left or right. In this case, only drawn right. And so the confidence interval is going all the way out to those 2.5 percentiles, leaving 5% outside. So 95% of the probability that a mean is located inside this bell curve is represented in that blue, whereas a much smaller chunk is represented by the standard error. So the standard error is essentially 68% of the bell curve. A 95% confidence interval is saying there's a chance that the mean falls inside this wider interval. That chance, 95%. This chance, 68%. Okay? So standard error is legitimate, but on the other hand, it is underrepresenting the amount of uncertainty we have in where the mean sits, because although it's usually unstated, it's only showing about a 68 probability of it being in here. We are 95% sure the mean sits inside this point in this confidence interval, which is more consistent with the way we have been using statistics so far. So the standard error actually can understate your variation in the mean. To put it another way, the standard error represents these means far more confidently, overstates perhaps the difference between these means compared to what you might express as a confidence interval. So if you're trying to present data and you wanted to convey a graph that implied that you had lots of confidence in your data and that there were really strong differences between the means, you might be using a standard error. But that is not fully consistent with the statistics that you might be using, whereas a 95% confidence interval is going to be more consistent with it, and a 95% confidence interval is going to be a bit more honest, I think, in showing where the data actually sit, I should say where the mean actually sits, because it's representing a broader interval. It makes it look a little more fuzzy, and you'd say, oh, that's a problem for me. I want my statistics really tight. But on the other hand, you could see how using the standard error could be perhaps biasing interpretation of the data. So I lean towards the confidence intervals over standard errors if I can have any say over it. Okay, so the confidence intervals can also be compared to the least significant differences, or LSDs as they're called. So these are also relevant for inference between means. The LSDs are even more directly related than confidence interval, but there's some reasons why I think a confidence interval might be more appropriate. A confidence interval is, according to Hector's book, not designed to show significant differences. It really wasn't the intent to show something that corresponds to a p-value test between means. It is showing you where there's a 95% chance of finding a mean. It indicates then some sort of approximate probability of differences between means. It isn't really trying to say this is a significant difference between means, but it's directly relatable. I'll show you in a graph in a few minutes. In other words, it's connected to our p-value kinds of tests, but only loosely, and it helps us let go of this binary p-value view that is rapidly falling out of favor these days. But it remains consistent because it has a representation of the probability of that mean, leaving only a 5% outside of that distribution. It's consistent with that 5% cutoff, in other words. And we can look at overlapping confidence intervals and essentially make inferences about the approximate probabilities of differences between means. So it in fact translates to our inferences of differences between means. the least significant difference is explicitly about the 95% confidence interval between means. So this is sort of like the standard error of the differences between means. This is related to a 95% confidence interval for the differences between means. And all that we really do with the least significant difference is take that interval, which, remember, relates to the difference between means, and we recenter that distance over each mean. So we're sort of taking an error bar that's about the difference between means and placing it over the top of each mean, which is a little odd in my mind, but okay. What we're essentially saying is that if those intervals don't overlap, then clearly you have a difference between the means. So it's much more specifically related to a p-value difference. But remember, we're supposed to be not too hung up about p-values these days, and so in my mind, the least significant difference test is not necessarily a more appropriate way to go, and I think 95% confidence intervals are helping us get away from the hang-up on a p-value, but are still relatable to p-values. So let me show you what I mean by the fact that they're relatable to p-values. Here I found a graph with some means and 95% confidence intervals. Let me see, this is the number of bird species at different latitudes. So you might say there's a general trend. You get fewer birds as you go north, except for this point out here. So I'm not really going to dwell on a general trend. What I'm going to focus on are comparisons between means with their confidence intervals. So let me see, this mean seems to be just below that interval, but on the other hand, this mean is inside the interval to the right. So that first mean being inside the interval to the right tells me there's not likely to be a difference between these two means, okay? So I can use this overlap pattern to help make inferences that are tied into the p-value kinds of comparisons that we might also make. Let me look at another pair, for example. These two, this error bar overlaps with the one on the left. This error bar looks like it just misses the mean on the right. So this mean on the right looks like it's outside of the error bar to the left and vice versa. So I would be pretty confident in saying that there is likely to be a difference between these, and this is probably comparable to a p-value of about 0.05 or so, where it looks like there's some separation of these two means, where the mean sits here and there's a 95% chance of finding it inside that error bar and inside that error bar. So the chances are of this finding this mean inside that error bar are very low. Chances of finding this mean inside this error bar are also very low. See how that's related to a p-value, but not hung up on exactly what the p-value might be. Okay, one more. Let's look at these two. They're clearly separated. The error bars don't even overlap, and so it's very likely that those means would be different, and so we're looking at a p-value that's probably closer to a 0.01 or lower even, okay? So we can infer something related to p-values. We're looking at the distributions of where the means are likely to sit, and so we can make estimations of what differences might exist. We can also look at general trends where there's a progressive kind of rough stair-stepping up in the error bars and the means, except for that point over there. So these confidence intervals are useful for looking at broad trends and imagining a pattern of where means sit inside error bars that are translatable to our other tests that we might be doing. And by the way, I would say that it's likely if you're going to present data on this and you wanted to make some of these point-wise, pairwise comparisons that I've been making here, you'd probably be doing some statistics in addition to just making a graph. So the statistics that you do, ANOVAs, t-tests, etc., would be the other measures that you could use to try to explain differences between means. It wouldn't be just on this graphic alone. So I think confidence intervals are a preferred way to go for representing the variation of means, but let's not forget that if you want to represent variation of the data itself, you can use scatter plots and box plots and means plus or minus standard deviations. But let's remember that that is assuming you have a normal distribution, because the standard deviation on either side should be symmetrical, right? A box plot's fine. In fact, very useful, especially if you have skewy data and you can't see they're nice and symmetrical on both sides. That would be represented by a mean and standard deviation. I'm not a big fan of standard errors because I think they can underrepresent the actual variance because there's a lot of confusion in the jargon. I like using confidence intervals myself because, like I said, they represent 95% placement of the means. We can make inferences about the differences, relate to other analyses we might be conducting, and they're not strictly wedded to this p-value criterion They're sort of on a sliding scale of p-values that help you understand more about probabilities and less hung up on a binary criterion. So I kind of like the 95% confidence interval approach myself. Least significant difference being tightly wedded to p-values and being something we're supposed to be steering away from with our new statistics. So hopefully that helps make some sense of error bars, box plots, standard deviations, standard errors, etc., etc. And hopefully you see what I think is useful for trying to represent some of these data. All right. I'll see you in class and talk to you next time. Bye.